Today we have a pleasure to welcome Doc Norton. Doc is a Pluralsight author, clean coders, contributor, frequent blogger, international keynote speaker, and a coach. Once a dedicated co-slinger, Doc has turned his energy toward helping teams, departments, and companies work better together in the pursuit of better software. Doc is also the author of Escape Velocity, Better Metrics for Agile Team, which is also the topic here today. So don't miss the chance to read his book. And now a warm welcome to Doc. Hi, Doc.
Hey, thank you very much for having me.
Oh, thank you very much for joining us. I'm sorry it couldn't be in person, but hopefully next year.
Yeah, me too. I am looking forward to those days for sure.
Yeah, we as well. So as I mentioned before, we always encourage people to ask questions during the session, and we will dedicate last 5 to 10 minutes, depending on how long your session is planned to last, to read the questions from the Matchabout platform. Okay.
Sounds good.
Good.
All right.
Okay. So, floor is yours, as they say.
All right. Great. Okay. So as mentioned, Escape Velocity, right? Better metrics for agile teams. I think a great way to start this off is let's talk about velocity in the first place. What is velocity? And I want to get some information from y'all to help with this. So I'm going to ask you to participate in a Menti. The URL is at the top of the screen, and there's a barcode. There's a code you can scan with your phone if you want to use that to go in and fill out, answer some of these questions. I'm going to switch over to the Mentimeter to try to. That's interesting. Okay. You can also get there with menti.com and use the code 3036517 This will live update, so hopefully we've got folks who are able to participate. And all I'm asking you to answer is, in your experience, does velocity have some of these attributes? We can see answers coming in. And as we can see, a lot of these are relatively low on our scale. While some of us may find that velocity is consistent from iteration to iteration, and some of us may find that velocity allows us to forecast several iterations out with high probability. Other things like it represents code in production, or indicates I have satisfied users, or helps me to accurately diagnose team performance issues, tend to be slightly lower scores. And based on that, come to the conclusion, in my experience, that velocity is useless. Well, all right, it's nearly useless, right? For most of us, velocity isn't stable enough to really be used reliably. For a lot of teams, it's pretty variable. It's interesting how many teams recognize that their velocity is highly variable and yet feel that it is good for forecasting at the same time, right? So it can't be predicted, yet it's good for making predictions. If it is stable enough, it's often disconnected from actual deployment to delivery. So velocity doesn't actually represent code that's in production. It often, for many, many teams, represents code that they believe at the moment to be code complete. If it's connected to deployment and delivery, it rarely accounts for other aspects of the process. So, what's the cycle time from request to when the work commences? What's the actual lead time from request to when the work is done? So it's actually not very good for larger scale predictions. And even in the cases where all of those things are happening, it doesn't tell you anything about whether or not the work that you are doing, predictably delivering, is actually of value to anyone. So it kind of leads us to the question, why is velocity nearly useless? And let's start with, instead of why, let's start with what. What is velocity? And I'm not going to do a poll on this one. We usually get pretty much the same answers over and over and over again in this. Every time I've given the talk. So let's just talk about what velocity is for a second. So the one thing that we pretty much know that it is, that we all kind of share this definition, is that it's work units over time, right? Whether it's story points over a sprint because it's more Scrum, or it's just stories over an iteration, or it is work completed in a given work cycle, whatever you want to look at it, right? That's velocity. But if you think about it for a second, that's actually speed, right? Work units over time is speed. Velocity requires a vector. So it's interesting that we chose the word velocity because it needs to be headed in a particular direction. So really, if we think about it, velocity at its core is work units over time towards delivery of value. Okay, so that seems all right, and seems like it's a relatively universally accepted definition of velocity. But what else is velocity? If we look at it in a little more depth, what else do we see? Well, one thing that's really important about velocity is that it's a lagging indicator. So lagging indicators tell us what did happen. They're actually really good at confirming long-term trends, but lagging indicators aren't very good at prediction. We don't tend to use lagging indicators to predict the future in any other endeavor, any other area of focus. Now, I have a picture here of an unemployment line because if the unemployment rate is a lagging indicator. So if the unemployment rate is rising, that means that the economy is doing poorly. We can know how it's trending, but we don't know specifically where it's going to go next, right? So they're good for trends over broad cycles, but they're not necessarily good for predictions. So let's look at a different lagging indicator. This helps a little bit, I think, to really kind of cement this concept. So this chart is sales in quarterly revenue for a subset of retailers in the United States, but this is consistent anywhere in any market in the world. You'll see a pattern something like this right there. Let's kind of zoom in on that. So when we look at this from any given quarter, you can't actually predict the prior quarter, right? This concept of yesterday's weather isn't really true, yet we can see a broader pattern, right? We know with fairly high confidence that Q4 is always going to be significantly higher than 3, which is higher than 2, which is higher than 1. We don't know exactly how much higher. We don't know exactly what percentage it's going to be or any of those things, but we can see this broad pattern. We can know that quarter 1 is going to be low, quarter 4 is going to be super high, right? And if we aggregate enough of that data together, we might be able to start to get some indication of the percentage difference between these. So we might be able to use a little bit of math to kind of figure out, but the truth is we need a lot of data before we can actually start doing those types of forecasts. All right, so what else is velocity? So lagging indicator, good for trends, but not good for actually prediction. What else is it? Turns out it's the measure of a complex system, right? And it tells us about the end result, sort of that system, but it doesn't tell us anything about the process by which the result was attained, right? If we look at this simple little diagram, and you've seen something like this before, there's an awful lot of things going on here. First of all, we have an awful lot of players. We've got product owners and scrum masters. We've got the team. We have the customer, right? And then we have all of these kind of ceremonies and things that are happening. So we're, before even to the left of this, which you can't actually see, of course, we have backlog management, and then stories are ready, and then they're actually brought into the sprint backlog or the iteration backlog, and they're prioritized, and we work on them, and we test them, and we have daily stand-ups, and on and on and on. And then at the end of this iteration, out pops some number that says we did N number of things, and that's our velocity. So it's a lagging indicator of a complex system. Now that's interesting, but it doesn't help me reason much about it, right? Like those are kind of technical words in a way. But I got thinking about this and said, okay, well, what else is a lagging indicator of a complex system that if I use that by analogy, I might be able to reason more about velocity. I might be able to think about it a little bit more clearly by using some kind of an analogy. It turns out that there's something that's a lagging indicator of a complex system that almost all of us are familiar with, and that is our body weight. Your body weight is a lagging indicator of a complex system. Right? You can agree that there are certainly inputs and outputs. There are things that you do, there are activities that happen. And all of those culminate together into what is your current body weight. And you can measure that once a day or multiple times a day or whatever you feel is the appropriate interval. And there you have it, right? So thinking about your body weight, things that affect body weight. Well, there's simple stuff that's obvious, such as your diet or your exercise routine. Right? Those are pretty obvious things. And when we ask people, what contributes to your body weight, people tend to answer those things: diet, exercise. But there's a lot of other things that actually are at play here because it is a complex system. So, your genetics, your current state of physical health, your current state of mental health, the environment that you live in, where you work, what stress levels you have, your social network. All of these things actually are influencers on your body weight. So, all right, complex system, lots of influencers. That's interesting. Now, if we think about body weight and velocity, it's interesting. Does any given body weight mean that you are healthy? If I were to tell you about a person that I know and to tell you how many kilograms they weigh, or how many pounds they weigh, would you know from that number that that person is healthy or not? And the truth is, within a certain range, no, you wouldn't know. You don't have enough information about that individual. You don't know what other factors are involved. There are folks that weigh quite a bit and are professional athletes that are in incredible shape. Another person that weighs that much might be morbidly obese. So if we equate weight and velocity, the question is, does any given velocity mean that your project is healthy? And again, the answer is no for the same reasons being it's a complex system. There's a lot of things going on. Velocity doesn't tell us enough about that. We don't know enough, given that number, about the team, about the work environment, about the customers, about the product itself. We don't have any idea based on velocity if a project or a product is healthy in any way. Now, back to body weight for a second. How might someone lose weight? Let's say that you want to lose 5 kilos. Some basic things you could do: you could reduce your calories. You could change your exercise routine, right? You could maybe get some more sleep, or you could cut back on certain types of foods. Those are all pretty reasonable ways that you could lose weight. But what if you were really focused on losing that weight? What if the only thing you were measuring was your weight, and that was the target you were setting? What else could you do? Well, you could consume nothing but amphetamines. You could stop drinking all liquids. You could smoke crack, or you could cut off your forearm. Now, those are ridiculous things to do, obviously, but the point here is really simple. Moving the metric in the right direction doesn't necessarily improve the overall health of the system, and it might even hurt the health of the overall system, especially when you're dealing with a lagging indicator. So back to body weight, or back to, velocity. How might a team increase velocity, right? Well, they could limit their WIP, they could reduce their batch size, They could reduce the number of dependencies between them and other teams. So they could reduce the amount of integration that's necessary so they could move to production faster, right? This is how a team might increase their velocity. But again, if you were focused specifically on velocity, if you weren't measuring other things, or if you felt pressure around velocity as something that's super important, what else might you do? Well, you could skip testing, or you could cut corners on internal quality. You could work more hours per week, or if you really wanted to just very simply increase your velocity, you just increase all of your estimates. The point here is simple and the same. Moving the metric in the right direction doesn't necessarily improve the health of the overall system, and it might even hurt it. This is a challenge in a lot of organizations. With good intentions or not, bosses set goals or they ask for improvements in indicators like this, right? They ask for us to increase our velocities. They're almost always guaranteed to create problems rather than benefits. Right? First of all, there's a law in economics known as Goodhart's law. That law states any observable statistical regularity will tend to collapse once pressure is placed upon it for control purposes. I'm going to say that again. Any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. Right? Lots of words. Really what we're saying there is when you set a target for a metric, I'm getting a lot of background noise. And now I'm getting someone testing their microphone. I'm still getting someone testing their microphone. So when you set a target for a metric, the odds are the metric no longer means what it once did, and therefore your target doesn't mean what it once did, right? So this law, which is applicable in our field, you set a target for a metric, that metric doesn't mean what it once did, and therefore your target doesn't mean what you think it does. Furthermore, properly incentivized, people will hit that target, but whatever means is necessary. These are known as perverse incentives, right? They're an unintended result contrary to the interests of the incentives makers. Okay, so this can lead to perverse incentives, right? And I think it's interesting how often you'll hear managers say that the employees gamed the system, right? And I want to get something straight with everyone right now. It's actually managers that game the system by setting goals for measures. The rest of what happens is just natural consequence. If you set a reward for the number of bugs found, you're going to get low importance duplicated bugs that don't actually add value, right? You're going to get arguments over whether or not that's truly a bug. If you set rewards for code coverage, you're going to get increased coverage, but you're going to get decreased test quality. And if you set rewards, whether it's actual bonuses or just encouragement for higher velocity, you're going to get more brittle code, lower test coverage, and more bugs. All right, so let's talk about how is velocity used, right? What are things that you use velocity for? And here's another area where I want to hear, again, from the audience. So same poll, and I will head over there. So how is velocity used? In this case, it's just kind of a free form text. Just a couple of words is all that we need, and you're welcome to answer multiple times. So if you think about velocity at your organization, how is it that you use it? Yesterday's weather, forecasting the next sprint, tracking team trends, focus factor for planning and velocity, forecasting. Excellent. I'm sure other answers will come in. This is the most common set of answers, right? So we're trying to plan with velocity, right? That's what it's primarily for. So let's head back here. And that's pretty much it, right? Typically with velocity, what we're doing is we're trying to plan an iteration. It typically has three key uses, right? It's a gauge when planning our iterations, sometimes referred to as making a commitment. So how much can we actually get into this iteration? It's used to determine if we're tracking to our iteration goals or release goals. And it's a means of forecasting, sort of, right? So let's look at that to track a release, right? You've seen these kinds of things, burn up charts, etc. And then some form of forecasting, usually because we get some question like this, right? Hey, what's happening? Yeah, I'm gonna need to know how long this feature is gonna take. Now, this is actually interesting. It's a common question. How long is this feature gonna take? Perhaps it's one of the most common questions that we get. And here's the thing, almost nobody wants to know how long it's gonna take, right? What they really wanna know is when will it be done? And these aren't the same thing at all, are they? So for using velocity for forecasting, and I said, sort of. Why did I say that? Well, how do we do this? We take our current velocity, or the average velocity of the past few iterations, right? And we divide it into our best current guess of the work that needs to be done. We graph it in some way, maybe, right? And then we have some kind of an extended trend line. And where those lines cross is where we anticipate that the work is actually going to be done. Right, that's pretty common. You might use a burn up, you might use a burn down, you might do something a little more simple, or maybe something a little more sophisticated. But the fundamental of it is the same. We're taking an average velocity over time, we're dividing that into the amount of work that we think is remaining, and we're using that to project approximately when this is going to be done. So, a couple of questions. Are these forecasts accurate? Now, the truth is they don't tend to be particularly accurate, right? We might imagine that they're precise, but they're not really very accurate. Are they definite? No, they are not definite forecasts. Are they probable? This is a good question. Are they probable? Maybe, right? They're possible for sure. How probable are they? We might not know when we're actually doing the math. So how much confidence do you have in your forecasts when you're using this common technique? And why do you have that confidence is another very interesting question. So let's look at exactly how probable is this technique. So let's get to probable. Let's take a scenario here. We have a team that has last three iterations, their velocity is 11, 10, and 9. Their backlog size is 130. Got it? Okay. What we also know about them is that the start date is today, and I'm going to give you something called a split rate. Let's not worry about that for a second. What we want to know is, will this team get this work done 13 weeks from now, which I believe to be January 7, 2022. Will the team be able to get the work done 13 weeks from now? And we can use kind of our standard velocity math, right? And we'd say 11, 10, and 9 average to 10. If we divide that into 130, we get 13. Therefore, the answer is yes, that if we start today, the team would finish this work 13 weeks from now. And agree or disagree, this is the technique that almost everyone is using for doing their forecasting. You might add in a little bit of sophistication around, oh, but people are going to be on vacation or whatever, right? But for the most part, this is the technique that folks are using. I want to show you a different technique that I think is far more effective. So this is actually a forecasting tool that's in an Excel spreadsheet that's available from the folks over at Focused Objective. Here's the URL on the screen. I'll leave that up for a second before I move into the actual demonstration of this tool. And we will make this URL available to folks after the meeting as well. All right, so let's head over to the tool itself. Okay, so here we are. If you remember, our average velocity was 10, and we're going to go ahead and put that in here as our low and high. It's just the average right now. Our start date is today. We have 130 units in the backlog, 130 points, if you will. All right. And when I put all that in, over here, what we're looking at is a probability distribution of the work actually being completed. And according to this, 1/6/22 is the date that this work will in fact be completed. And that matches 100% with our estimate based on standard velocity math. But let's take another look at this. Remember that our low was actually 9 and our high was 11. Just 9, not 9i.
Hi, Doc. Sorry to interrupt you. I've sent you an email in chat. I thought you didn't see it, but you are not sharing your presentation. Is it the way you want to do it, or?
Nope. Of course, I want to share the screen.
Yeah, you probably haven't noticed that I sent you in chat. Okay.
Nope,
good.
I did not notice. Okay.
Okay.
All right.
Good.
Okay, good.
Sorry to interrupt you.
No worries. All right. Mostly up until now, it's been animations and cute stuff. So this is the important part. Thank you for letting me know. Okay. So what we're doing is a forecast, right? And we had the start date is today, 130 points in the backlog. And our velocity, we said was average of 10. But actually, now we're saying, hey, look, actually the velocity over the last 3 iterations was a low of 9 and a high of 11. And what I want you to see is over here, what's happened is suddenly we're seeing that, oh, wait, we have a 50% probability or less of actually getting the work done before the 7th. And more realistically, it's going to be a week later than that, based on the high and low of our most recent velocity. Now, the way that this tool works is, and I won't get into the fine-grained details, but the way that this works is it's a Monte Carlo simulation. So it takes your data and it actually simulates 500 project completions using velocities in the range between 9 and 11, burning against your low and high work remaining estimates, and it shows, and it maps all that onto a histogram and creates a probability distribution. Real quick, for those of you that are looking at this going, well, wait a minute, how do we know that the distribution is correct? This isn't Gaussian. You're right. We're actually using a shifted Weibull curve as the base for this because that is consistent with how projects flow. If you don't know what I just said, don't worry about it. This is a very accurate way of looking at when do we think this work will actually be done and putting to probability distribution. Now, what's really nice about this is you might notice right here, I have this set to estimate, which is using these 2 numbers. But what I can do with this tool is I can actually tell it, here's the history of this team's throughput. So there's our 9, 10, and 11 again, right? But we can see that they also had some 6s and 8s, and they had a 14 and a 16, and they even had an 18 at one point. So we can see that their velocity or their throughput is pretty variable. But when we actually tell it, hey, don't use our estimates, use the actual data, it recalculates. And it turns out that depending on the confidence interval, the probability that we want to go with, instead of it being 1/7, which is what we were asked, really we only have about a 50% probability that it's going to get done on time, for 1.7, we're probably much better off saying, hey, between 120 and 127, right? If we want absolute certainty, than 210, but we're probably better off giving dates in this range. And of course, when we give dates that are in a 85 to 95% probability, what we're saying is we have an 85 to 95% probability of coming in on or before that date, right? So we want to be careful, because oftentimes what happens when we give these kinds of probabilities, which are safe numbers to give, and then it turns out that we finish on the 13th, then people start to say, oh, you didn't estimate it correctly because you got it done too soon. This is all about probability, right? Okay, so let's move on from that. I can't seem to, there we go. All right, I'm going to go through these really quick. This is just another example of it. Okay. So now here we are, we're back at work. The manager shows up again, says, I hear your velocity's all over the place. I'm going to need you to fix that. Okay. So the more variable the velocity, the worse the forecast due to lack of consistency, right? We saw that with our Monte Carlo simulator. Velocity's all over the place. Our probability distribution gets bigger and bigger and bigger. It gets further and further spread apart, right? As our velocity starts to tighten, then our ability to actually get to predictable, improves. So I'll ask you another question. So here's a chart, a variable. This is a chart of velocity for a team over the course of 10 iterations. This is not the same data as our prior team, but you get the idea, right? The velocity chart for the team over the course of 10 iterations. My question to you, what's wrong with this team? What is wrong with this team? And we will use the Mentimeter again. And just a word or two, just briefly, if you saw a team with that kind of variability in their velocity, what might you conclude about that team? What challenges do we suppose they have? They underestimate. It's difficult to say. Yep. COVID. They're estimating wrong. They have too many dependencies. They may have a different number of team members. So maybe they're in some kind of a discovery phase, or maybe they had more team members earlier, now they don't, or maybe their team members are variable. Underestimating. They're not breaking up their stories well. A lot of dependencies uncleared before the sprint starts. They're bad at estimating, bad story pointing. Yep. Shifting scope, lots of dependencies. Excellent. All right, lots of good answers, good insight based on the data that we have. And that's actually kind of the point, right? Based on the data that we have, we're guessing. We don't actually know what's wrong with this team at all, right? So Deming tells us setting quantitative goals doesn't matter. Fix the methods that are underlying those goals, right? So if we're going to do that, if we're going to say, hey, look, let's not look at the goal and then try and figure out what's wrong with the team. Let's fix the method by which those goals are attained. Let's look at some common causes of variable velocity. What are things that cause teams to have variable velocity all over the place? And you actually mentioned several of them already in your answers, right? One that I see that doesn't get mentioned a lot, and I think is actually a really significant contributor, is deferred maintenance. I refer to this as deferred maintenance. Some people call it technical debt. I don't, because technical debt has a specific definition, and deferred maintenance is not part of the original technical debt definition. But basically, what's the deal? The team feels like they don't have time to clean the code, they don't have time to refactor, They don't have time to upgrade the infrastructure, et cetera. So all of those things, cleaning the code, refactoring the code, upgrading the infrastructure, those are all maintenance issues. They all get deferred, and that ends up gumming up the system, right? They end up causing the system to move slower and slower and slower. And ironically, all of that is done in the name of speed. Deferred maintenance gums up the system and actually causes it to move slower. Now, if we know this to be the case, and we do, what might we be able to measure that would help us? Now, some folks say, well, we're going to measure our technical debt. That's an interesting suggestion, because we don't have a definition of technical debt. And you might say, of course we do. Say, great, go back to work. I want you to pull your team together, and I want you to have them write on a piece of paper to themselves exactly what is technical debt. And then I want you all to share your definitions, and I will almost guarantee you they are not the same. If you get specific, it turns out that we all disagree. All right, so what can we measure? That's what is important, right? So one thing that we can actually measure, and it's relatively simple, is code complexity. Code complexity, you can use cyclomatic complexity, you can use ABC complexity, it doesn't really matter. There are tools that do this. And basically what we're measuring is the nodes and edges in a code tree. What? We're measuring the number of conditionals in the code. More or less, it's a count of independent paths in the code. This measurement was actually originally used to try and figure out how many tests we should have around code. But what we discovered was that there is a positive correlation between code complexity and defects. A positive correlation. The higher the complexity, so the more conditionals in your code, the more likely a method is doing too much or has low cohesion, the more responsibility the method has, or the lower the cohesion, the higher the likelihood that there are defects lurking in there. And it turns out that a lot of conditional code can be collapsed with various forms of refactoring. And when we do that, the code becomes more clear, more maintainable, et cetera, right? So measuring code complexity is a way to measure deferred maintenance and to know if the code is in good shape or not. All right. What else could we measure? Well, we could measure escape defects. Now, escape defects are the defects found in production. It's important that we make this distinction. A lot of organizations measure defects that are found in QA or in other pre-production processes. I think that's a mistake because that is all part of your internal process of delivering code, right? Figuring out before it gets to the customer that, oh, hey, this isn't quite right, isn't a defect. That's just a part of our process. It's when it gets out into production that it's actually a defect. So if you want to continue measuring those internal ones, great. What we want to concern ourselves with is escaped defects, those that are actually in production. And let's just kind of look at those over time. Now, this is informative, but it can be slightly misleading. So what we're looking at here is iterations, over a time period and the number of escape defects. The reason this is misleading is what we don't know is how much code, how many points, how many units did we deliver in those same iterations? And that can make a difference, because if we look at our throughput in those iterations, we see a different graph. So let's take those two graphs, escape defects and throughput in a given iteration. Let's turn them into a ratio. And now what we have is something that's telling. Right, what this tells us is basically the percentage, if we have it gives us a percentile for defects by throughput. And so now we know that the second iteration in May was a relatively high defect count, even if when we go back, that second iteration in May didn't look any different than June. Still high, but not, not all that significant compared to June. But when we actually combine them, we can see that, oh, okay, something happened here. So this tells us, based on how much we're moving into production, what's the relatively how many defects are we moving into production? And it gives us a better sense, and we can actually watch this over time for trending down, right? Okay, so that's enough about deferred maintenance. What else causes variable velocity? Well, batch size, and I think someone mentioned this in our share there, right? Someone talked about not breaking stories down enough as one of the reasons, right? So variable story size, consistently large stories, stories that don't get delivered until the feature's actually done. So now what we have is like, oh yeah, we're working on all these little tiny stories, but nothing's getting actually delivered until the whole feature is done. So that feature becomes a batch, and the stories we're just kind of pretending that we're doing something. Features that don't get delivered until the release is ready, right? So a release is another batch. So oftentimes I see these organizations where teams are working in iterations, and they're decomposing their stories, and they're doing all of this stuff, but they're only releasing every 3 months or 6 months. So it turns out they're still working in great big batches in one way or another, right? Inconsistent batch sizes, wherever they may be, whether it's the size of the story, the size of the iteration, the size of those all cause variability in delivery, which results in lower predictability, and might even result in or indicate bottlenecks, right? The bigger the batch size, the greater the risk, wherever it is that batch size appears. All right, so I think you all pretty much know how to measure the size, right? How big are our iterations? How often are we releasing? Those are all kinds of things. So if we look at, we say, hey, release frequency is one way of, is one indicator of batch size, right? Assuming all other things equal, the more often we release, the necessarily smaller the release, right? So if you're releasing, once a quarter, and all you do is change that to once a month, it is absolutely necessary that each release is smaller than the quarterly release used to be. So you have automatically reduced that batch size, right? So we can effectively use release frequency as a proxy for release size or batch size. Our release size is our batch size. Small releases beat big releases every time, right? You've got higher optionality, you've got more flexibility, you're learning faster. You actually have more safety when you release more often. Yes, more safety when you release more often. Small releases have a smaller surface area and therefore a smaller impact. Each of those releases actually provides less risk than putting them all into one great big release, right? Something else we can measure that is related to batch size is something called coupling. Now, coupling is a code metric, just like complexity is a code metric, and it can be determined through simple static analysis. There's plenty of tools that do this, and it basically refers to the dependencies associated with a piece of code. So there's afferent and efferent coupling. We don't need to really worry about those, but afferent is basically the number of things that are dependent on me, and efferent are the number of things that I am dependent upon. Now, when we look at dependencies, coupling, when we run our static analyzer, it usually shows us dark spots, which is our classes, and then lines between those classes, which shows the dependencies. And for a lot of organizations, their coupling tends to look something like this. That's not really true. It's a bit of a joke, but you get the idea. What we want is low coupling, right? You want very few lines between those nodes. Let's look at something that's a little more, there we go. All right, so this is a little more realistic. This is maybe what high coupling looks like. So what we have here on the left and on the right are things in our code base. Let's say that it is the shopping cart and the cash register, right? Or maybe it's the employee management and the payroll system. And let's go with shopping cart, right? So these two things seem to know a lot about each other. You can see a bunch of lines between them. And it means that changes to the cash register would potentially break the shopping cart. And I think we can agree that doesn't really make sense. In addition to that, both of these seem to have an awful lot of connection paths internally. Now, this happens a lot, especially when we're moving really quickly, trying to get those points across the line. The code starts to look like this over time, where there's just these little dependencies. Oh, I just need to call that one thing. Oh yeah, I just need to know this one thing, right? And the next thing you know, you have these modules in the code that can't be independently deployed from one another. What's interesting is we see this all the time as organizations are moving to microservices. You now have microservices that are coupled through data and connections like this. They're not actually independent. They still look the same. So what we want the team to do, one, is there's some techniques that they can use. One, they can isolate some of the behavior. And then you can actually start to separate the internal. And this is all possible through basic refactoring. And now you get into something that is low coupled. And with that, you actually have the ability to deploy each of these things independent of one another. And now you can move much faster because you're basically able to deploy in smaller batches. So again, coupling actually relates to batch size. Right? What else? Variable velocity, work in progress, right? This is one of the most common things is because teams just have way too much going on. And that actually causes them to not be able to get things done as quickly. I'm going to go through this relatively quickly because I know that folks know about work in progress, but I just want to show a good model here. So stop, starting, start, finishing. Let's look at 4 tasks of 8 hours each. Now, how do I know they're 8 hours each? I don't know. It's black magic. We're going to pretend that you can estimate complex things, and that's a whole nother talk. We tend to start them all at once on a team, right? And we believe that those 4 things will be done in 32 hours. Now, the reality of it is that when you are context switching, there is actually a tax. There's a tax for context switching. And studies have shown that tax is approximately 20% for each new item. And it's compounded, right? So in reality, it will take approximately 48.75 hours to complete all 4 tasks if you're trying to task switch them and do them, all basically at the same time. Whereas if we finished them one at a time, we would actually get to or very close to that 32 hours. Yet we have this tendency to try to do things all at once because we want to keep making progress. I need to hear back from the database administrator rather than actually calling them or going to their desk or getting them on FaceTime or Teams or whatever. I'm going to shoot them an email and then I'm going to go start something else, and then that gets held up and blah blah blah. And the next thing you know, here we are. All right. So I want us to take a look at, as we think about all of these things, I want to show you some keynote flow diagrams. And I know that you're probably familiar with this as well. When I first started doing this talk, people weren't familiar with them, but now they are. But I want to just give you some insight. A lot of folks see these and they like them, but they're not sure how to read them. So let's go through that really quick. So this is a cumulative flow diagram. And let's just see what we can do. So this tells us a lot of information in one simple snapshot. So here, that's the amount of work done, and that's the amount of work not done. That's helpful, right? We can see the average lead time, the amount of work in progress at any given time. We can see the average lead time for any given iteration. We can see the average cycle time, right? And we can see changes in scope, all by looking at this. So it's a very useful insight into what's happening for the team. And for the team that's operating relatively well, this graph is relatively smooth lines that are moving together up and to the right. For a team that's not operating so well, you're going to see something slightly different. And that's what we're going to look at now. So if you remember this team, this graph, we asked what was wrong with this team. We couldn't say for sure, right? We took a bunch of guesses. It might be staffing, it might be COVID, it might be story size, it might be, but we didn't really know based on the information that we have. We can't tell from this. So let's look at that exact same team, that exact same data, but we're going to look at it from a different perspective now. Here's their cumulative flow diagram. And I don't have a poll for this. I want you to sit and look at it for a second. I want you to take a guess at based on what you can see, what do you suppose is the issue for this team? What you might notice is that the ready for approval, the green, gets really thick and then suddenly gets really thin again. And then it gets really thick and then suddenly gets really thin again. Now, this is an indicator, right? It's not moving smoothly up and to the right. Something is happening. And what's happening is work is getting trapped in ready for approval. What we discovered with this team was that their product owner was actually a traveling salesperson. And when they were on the road, they did not have time. And so what would happen is when they came off the road or when they felt really pressured, they would go through and they'd review a bunch of stuff and they'd approve it all at once. And they'd also bring in a bunch of new work. So all of our guesses about estimation and team size and blah, 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 that wasn't it at all. It had nothing to do with the team. You can actually see that the team, they're in progress and in testing. It's actually pretty consistent. They're doing a really good job of managing their WIP and everything else, but their product owner was not available and resulting in this. And until we pulled out the cumulative flow diagram, the assumption was consistently that it was somewhere on the team, not somewhere else in the flow. Right, so super helpful. I want to finish with a thought that I think is really important. Metrics are not just for managers. Metrics are for the teams. We want the team to be able to understand what's happening and make their own decisions. So thank you very much for attending. I'm going to move to the next slide here, just so that you can, if you send a blank email to that address with the subject line Escape Velocity, all one word crammed together, I will send you these slides and a bunch of resource links that were behind the studies that were done here and the information that supports this.
Thank you very much. It was very pleasure for us to have you here today. This is the first time that we're working together, and I hope this is just the beginning. So thanks a lot. We had a couple of questions, in Match About Q&A section, but unfortunately we're out of time. So if you wish, you can go. That's okay. It was worth it. If you wish, you can go through Q&A and answer these questions if you want. Okay, so thank you again, and hopefully we'll have an opportunity soon to work again together.
Thank you very much.
Thanks. Bye.